In this video, I'll be going over my solution to the 2020 AIME I Problem 14. So we're given a polynomial q of x, a quadratic polynomial, and it has a leading coefficient of 1, and we have the equation p of x equals 0 with the roots 3, 4, a, and b, and we're asked to find the sum of all possible values of a plus b squared. Okay, so we know that p of a equals p of b is equal to p of 3, which equals p of 4, which equals 0. Okay, so let's let p of x, since p of x is a quadratic with the leading coefficient of 1, then we can write it in terms of its roots. So let's let p of x equals x minus r times x minus s, okay? And then let's call p of a q1, p of b q2, p of 3 q3, and p of 4 q4. So then we have p of q1 equals p of q2 equals p of q3, which equals p of q4, which equals 0. And we know from our established definition of p of x that this has roots of r and s, right? But if we have p of all of these things equals 0, then q1, q2, q3, and q4, all of these are also roots of p of x, which we can't have because p of x is a quadratic. So it can have at most 2 distinct roots. And so in order for this to have 2 distinct roots, a pair of one of these has to be equal to each other. So either q of 1 has to equal q of 3, and that equals r or s. So if we set q of 1 equals q of 3, for example, and then we could set that equal to r or s, let's just choose r, then our other pair would have to be equal to s. So our other pair equals each other, and that equals s. So we have to have something of this sort. In order for our condition for this to be a quadratic to be satisfied, a pair of these has to be equal to each other, right? And so let's get rid of the q's again. That was just to explain how we have to have pairs equal to each other, right? So so we basically have two cases. Let's do casework on p of 3 and p of 4. So the first case is if p of 3 equals p of 4. If p of 3 equals p of 4. Okay, and so let's see, then we have 3 minus r times 3 minus s equals 4 minus r times 4 minus s. And so let's expand this out. So we get 9 minus 3r minus 3s, and then the rs is canceled out, equals 16 minus 4r minus 4s. And so then we get 7 minus r minus s equals 0. And so from this, we get r plus s equals 7. Okay, so let's stop here. This is an AIME problem, and we're talking about the sum of roots, right? So it's pretty obvious that we're going to have to use Vieta's formula somewhere. And I think the most obvious application here would be to write the coefficients, the first two coefficients of p of x, right? If we have p of x, then we're going to have x to the power of 4. And then we establish that p of x equals x minus r times x minus s. So the other coefficient is going to be negative 2 times r plus s times x cubed. And then some other complicated stuff added on. What we really care about, though, is this coefficient. Because this tells us that the sum of the roots of p of x, which in this case are a, b, 3, and 4, this sum equals 2 times r plus s. And we've already established that r plus s equals 7. So then this equals 14. And so 14 minus 3 plus 4 equals 7. So a plus b has to equal 7. And if a plus b equals 7, then for this case, a plus b squared equals 49. So that's what we got for the first case. Cool. So for the second case, is just basically the opposite. What if p of 3 is not equal to p of 4? So if p of 3 is not equal to p of 4, it doesn't really matter which pair we choose, because we're just going to end up with the same values for a plus b. So let's say without loss of generality, we have p of 3 equals, let's say, p of a, and we can choose either rs, let's just say we choose r, and then we say p of 4 equals p of b, which equals s. Okay, so we're going to worry about the a's and b's later. Let's first focus on these parts. So let's write out our equation. So we have 3 minus r times 3 minus s equals r, and then we have 4 minus r times 4 minus s equals s. And so let's expand each of these equations out. So then we get 9 minus 3r minus 3s plus rs equals r, the first equation. And then here we get 16 minus 4r minus 4s plus rs equals s. And so since 16 is larger than 9, let's subtract this equation from this one. And so we get 7 minus r minus s is equal to s minus r. And so then we get 2s equals 7. And so s equals 7 halves. Okay, so let's plug back s now. So then we have 4 minus r times 8 halves minus 7 halves, which is 1 half. And that equals 7 halves. So then we get 4 minus r is equal to 7. So then r equals negative 3. So this is what we get. Okay, cool. And so now let's see. So then what's r plus s? So r plus s equals 7 halves minus 6 halves, which equals 1 half. And then from the Vieta's formulas, relationship we established before, we know a plus b plus 7 equals 2 times r plus s, which is 1 half. So then a plus b equals 1 minus 7, which is negative 6. And if a plus b equals negative 6, then a plus b squared equals 36 for this case. And so we're done. We have the only two possible values for a plus b squared. And you can also try this out yourself, because it doesn't really matter which pairs you choose and which pairs you set them equal to. You're always going to end up with the same value for a plus b. So a plus b squared equals 36, or 49. And so now it's asking for the sum, so we just add them up. And so our answer is 49 plus 36, which equals 85.